Hello, everyone. Today we're going to be extending our conversation on non-ideality by looking at some of the applications of our internal pressure that we developed last time. And hopefully we'll be building up a discussion of isothermal compressibility. So this is going to be focusing in on a little bit of some of the more non-traditional ways of how we can examine the energy of a system besides an ideal gas. So last time we ended up building up a fairly general description of how the internal energy changes with volume and temperature. And essentially we have a volume dependence based on the internal pressure, which is going to be a feature of IMFs and non-ideality. And it's going to depend on temperature based on heat capacity, which is another measure of saying, where can I store my energy before I have to start putting it into translational motion that can be measured as temperature. So one of the applications we can look at is, say, looking at how at the temperature dependence of our internal energy when we're now working under isobaric conditions. So this is an important kind of comparison to enthalpy, because enthalpy is again looking at heat under isobaric conditions, but this is again internal energy under isobaric conditions. So analogous, but in a very important difference. So if I'm looking at this change under isobaric conditions, one of the quick tricks I can do is take this equation and then simply divide it by the change in temperature and limit it to isobaric conditions. So we get our key variable here, change in internal energy with temperature under isobaric conditions. But we also generate some other variables like the change in volume with temperature under isobaric conditions and the change in temperature with change in temperature under isobaric conditions. So not too surprisingly, this term actually gets rather simple, and we're more or less just left with the other two. So we've already developed a description of how we can get at isobaric isothermal compressibility and heat capacity. Now we need a good description of how our volume changes with temperature. So as usual, if I have a new set of variables, I'm going to try and ascribe a new term for it. In this case, what we're going to be looking at is called the expansion coefficient. And one of the things we have to watch out with the change of volume with temperature is we have a size extensive property divided by a size intensive property. So we'd rather like a expansion or a coefficient that doesn't depend upon the size of my system. And this is essentially accomplished by dividing my change with volume by the actual volume of the system. So another way of looking at it is it's the percent compressibility with a change in temperature. So if I increase the temperature by say 1 degree, what percent does the volume expand? And so this can actually be a rather useful metric. And again, we would typically expect this value to be positive because in general, as the temperature increases, so will the volume of the system. So again, thus again, the expansion coefficient. So we can go ahead and try and treat our expansion coefficient for, say, a nice simple case to get an idea of limiting conditions. So let's go back to our ideal gas. And in this case, we can essentially substitute for the volume R nRT over P. So substitute in the ideal gas law and then look at the temperature dependence under, here's the very important part, isobaric conditions. And because I've got isobaric conditions, I now know that N, R, and P are all going to be constants. So I can pull them out front. And then this just leaves me with the change in temperature with temperature. So again, this time we get very lucky and this term will end up canceling out. And so what we can do is then simplify this to our change in volume with temperature is equal to nR over P. And then using the ideal gas law again, we can substitute this back to V over T. And so this is actually a very useful kind of metric. We expect our change of volume with temperature to actually be equal to the ratio of volume to temperature itself, which can be a little bit surprising, but is a very useful metric. And again, remember that this only holds for an ideal gas. However, this is again a size extensive property due to volume. So to make it a size intensive property, I divide by volume. And it turns out that for an ideal gas, the expansion coefficient is related to the inverse of temperature. Now, this is actually kind of a cool sort of metric, but it's always worth acknowledging what the heck does this mean? So in this case, what I would expect is if I have a very low temperature, so 1 over a relatively small value, say 10, under this conditions, an ideal gas has a relatively large expansion coefficient. So if I have a 10 Kelvin system, at the point I'm probably dealing with helium, I have a 10% increase of my volume for every essentially degree my temperature changes. Now, as the temperature increases, essentially my system becomes much less temperature dependent. And by the time we get to very high temperatures, I need to have a much larger temperature change to get a similar expansion of my gas. And this again should hopefully make sense because at this point my gas should already be fairly large. And so any percent increase is going to take a significantly more energy. But again, it is worth noting that this expression only holds for an ideal gas. And in practice, you often need to measure the expansion coefficient mechanically for any sort of non-ideal system. You can extrapolate alpha values for other real gas equations, such as van der Waals. But once you get to condensed phases, such as liquids or solids, you're often going to need to calculate this directly or from direct measurements. But what this allows us to do is substitute back our dV over dt is going to be equal to alpha v back into our original equation. And what we get is the change in internal energy with temperature under isobaric conditions is going to be related to the internal pressure times the volume times the expansion coefficient plus our heat capacity. And again, at this point, we're actually in fairly good shape of trying to determine our isobaric change in internal energy with temperature, because CV, alpha, and internal pressure are all well-measured properties for many substances. And then V will be dependent upon the actual sample you're measuring. So again, we are going to see a certain size extensivity dependency on this, on our energy change, which again makes sense because this will be our absolute internal energy, not our molar internal energy. So again, a notable importance. And similar, our heat capacity is not the molar heat capacity, it's the absolute. But what's really wonderful about this equation is that it's actually fairly general. We made no assumptions about the ideality of our system or even the phase of our material. So this will actually hold for solids, liquids, and gases. So again, a quite useful sort of metric. And again, all of our various properties can actually be measured experimentally. And again, this is also another method which we can try and, if we are able to determine our change in internal energy with temperature, it's another metric of trying to get at our internal pressure. And again, this is also going to give us a certain degree of utility, because by measuring the difference in between our change in internal energy with temperature under isobaric conditions and under isochoric conditions, we can directly get at our uh, internal pressure. Now, one of the things that is actually worth noting is that for an ideal gas, we've already shown that we are going to have an internal pressure of 0, which means that our isochoric heat capacity is going to be related to our isobaric change in internal energy. So again, under ideal conditions, it won't matter, or change in internal energy won't matter whether we're doing it isobarically or isochorically, which is a very useful thing to know. But it is worth noting that this does assume ideal scenarios. Under non-ideal scenarios, we are going to see a deviation in between isobaric and isochoric conditions. It is also worth noting that we have another analog to our expansion coefficient, and that's our isothermal compressibility, which is looking at the change in volume with pressure under constant temperature instead of the change in volume with temperature under constant pressure. So again, when you pair these two together, you're going to have a lot of power. But again, it is worth noting that we have this derivative is going to be size extensive. So to make it a more robust size intensive property, we turn it into a ratio of volume change by dividing by the volume of the system. One of the other important things to note is that we have a negative sign out front. And one of the reasons why is, in general, as I increase the pressure on the system, I expect the system to become smaller. So in general, we'd expect this derivative to be negative. So to give us a positive isothermal compressibility, we will go ahead and flip the sign by putting a negative outside of our derivative. Now, one of the reasons why the isothermal compressibility is actually quite useful is because it gives us another metric to relate volume, pressure, and temperature change, which can be paired together to look at the relationship in between all three possible variables, looking at using the triple product rule. Yes, calculus strikes again. So a good way to try and look at how you use the triple product rule is, say I'm trying to relate three variables: volume, pressure, and temperature. And so what I do is I then just cycle through the variables. So I move pressure up top, volume to being what's held constant, and then temperature to becoming the dependent variable. And then there's your next term. And then you do the same thing again. And it's worth noting, you can rotate these variables clockwise or counterclockwise as long as you do a constant rotation. For example, I can move temperature up top, volume to the bottom, and pressure as what's being held constant, and I get this term. So again, you can generate a triple product rule by just rotating your variables through till you have all three permutations. And it turns out when you do that, that equals -1. Now, one of the reasons why the triple product rule can actually be quite useful is, let's say I'm trying to examine the change of volume, pressure, and temperature. Well, it turns out that each one of these terms has its own specific utility. So, for example, it turns out that volume over pressure change is the same thing as my isothermal compressibility. Ta-da! So all I need to do is move a negative V out front, and I can substitute in. We see a very similar thing with over here. We have the inverse of change of volume with temperature under constant pressure, which is the same thing as the inverse of our expansion coefficient. So we have 1 over alpha V over here. And all that leaves us with is one last undetermined variable. So it turns out that using the triple product rule, I can determine how pressure changes with temperature under isochoric conditions by moving all of my known variables to the other side, let the negative signs and the V's cancel, and it turns out the change in the isochoric change of pressure with temperature is going to be related to the ratio of my expansion coefficient over my isothermal compressibility. So again, this is actually another kind of useful way we can start playing around with our variables, because under certain times, we might find certain of these metrics to be quite useful. For example, if I'm heating up a can of soda under, say, isochoric conditions, I might want to know what sort of pressure I'm building up. And again, it's worth noting that this will hold under a non-ideal case, as well as just a simple ideal situation. So again, one of the real powers of the isothermal compressibility of these variables is their ability to be used under non-ideal scenarios. But let's go ahead and say, I want to try and evaluate my isothermal compressibility for an ideal scenario. Well, in this case, I'm going to do a very similar trick to what I did last time. And since I'm looking at the change of volume with pressure, I'm going to substitute in my ideal gas law. All right, this works so far. Now what I can do is, since I'm looking under isothermal conditions, N, R, and T are all going to be held constant, because again, closed system and isothermal conditions. So all of these are constant variables. They're going to get hauled out front. And then all I'm left with inside is the change of 1 over pressure with pressure. So we get to take a simple derivative. But in the meantime, you might notice that if I've got an ideal gas, nRT over V actually simplifies quite nicely. This is the same thing as pressure. So I get negative pressure out front, and inside the derivative of 1 over pressure is negative 1 over pressure squared. Go ahead and cancel out my negative signs, cancel out one of my pressure terms, and it turns out for an ideal scenario, my isothermal compressibility is related to 1 over pressure, which again should hopefully make sense. The more pressure I already have applied to the system, the less change I'm going to see in the volume if I add that same amount of pressure. And so another way of thinking about this is I'm going to see a much greater change in volume if I go from 1 bar to 2 bars than if I go from 10 bars to 11 bars. So again, hopefully that kind of makes sense. And again, this ends up resulting in a fractional change of the volume for an ideal gas that's going to be inversely related to the pressure of the system, just like we saw an inverse relationship in between the volume of the gas with temperature to the temperature of the system. And again, hopefully all of this kind of makes sense from what we saw with our simple gas laws of Boyle's and Charles' law with inverse relationships in between volume, temperature, and pressure. Now we've essentially built up a whole series of variables for how my system, how I expect the volume of my system to change and what sort of relations this might have to energy. So let's go ahead and try and put this to kind of use to relate to some differences in our heat capacities. So we've already looked at the difference of our heat capacities for an ideal system, where Cp minus Cv. Now let's go ahead and try and examine this in a little bit more detail, but we're going to essentially check in with the ideal gas law along the way just to make sure we're on track. So I go ahead and can start by relating these to change in enthalpy and change in internal energy. And so when I do this, I'm going to use the trick that enthalpy is the same as U plus PV. And then I can go ahead and pull out my PV term, collapse my change in internal energy over temperature. And then what we end up having left is the difference in between our heat capacities is going to, using the ideal gas law, again, that PV is equal to nRT, take our first derivative again. nR is constant, and this leaves us a dt over dt, which cancels out. And we get our good old friend back, that the difference in between our isobaric and isochoric heat capacities is going to be equal to N over R. Or again, the difference in my molar heat capacities are just going to be equal to R. So this is actually very useful in that it confirms our findings from what we analyzed with monatomic and diatomic ideal gases. Now let's go ahead and try and solve this again for a general case. So in the general case, what we see is the difference in between our heat capacities gets a little bit more messy. And it's worth noting that we actually need to make use of entropy in order to solve this expression completely. And so this proof is a little bit beyond where we are right now. But for now, just take my word that the difference in our heat capacities is going to be related to our expansion coefficient, our isothermal compressibility, as well as the temperature and volume of the system. Now, since I have an ideal gas, my expansion coefficient is equal to 1 over T, and my isothermal compressibility is equal to 1 over pressure. So I can then substitute in with a pressure up top, temperature squared down below, and then TV. So then I can go ahead, cancel out my temperatures. And so I get PV over T, which again, using the ideal gas law, gets me back to N over R. So again, we get back to, this is a good way to show that even though we don't know how to prove this general expression yet, but again, it does simplify to something we already know how to be true. And again, helps us illustrate that the differences in between our various heat capacities are indeed going to be real, and they're going to show a dependence on expansion coefficient and isothermal compressibility, which by their natures are going to be dependent on how ideal our system is. So again, we do see that CP and CV are going to be significantly different if I'm non-ideal. But it is worth noting that once we get to condensed phases, again, we're going to see this whole expression start to drop towards 0, largely driven by a smaller expansion coefficient, because it turns out that if I heat a solid, it tends to expand a whole lot less than a gas. But again, this really helps us reach beyond where we've been at for just working with ideal scenarios. So next time, we're going to be trying to apply some of these general non-ideal ideas to enthalpy. Till then, take care.